In this webinar, we'll be presenting the research of Adriana Mantilla-Salas about the integrated reservoir characterization using high-definition frequency decomposition, multi-attribute analysis, and seismic forward modeling. Adriana did her master's at the Imperial College in London, and she spent 3 months with us during this summer running the independent project, the results of which will be shown to you today. The aims of this research were to perform a reservoir characterization using advanced seismic techniques and mitigate risk and potentially enhance the success of hydrocarbon exploration. In this research, she did try to evaluate the elements of the petroleum system, that is reservoirs or seal and trap, and aimed to explore the frequency responses, or in color blends it's the color responses, and investigate what they are related to, how they can be modeled when we change different morphologies of the rocks and different fluid and rock properties. The final aim was to validate a methodology for prospect de-risking and uncertainty mitigation. The research was carried out, geographically speaking, on the northwest offshore Australia in the northern Carnarvon Basin. This is a huge area. It's a very hydrocarbon rich area. It's been in exploration since 1953, and predominantly gas fields have been found, although there are quite a few oil fields as well. This particular data set is the Chandon data set, which covers nearly 900 square kilometers. And there are 4 wells in this area, Chandon 1, 2, and 3, and Yellowglen-1. As you see, they've been drilled in a time frame of 5 years. Geologically speaking, this area is part of the Exmouth Plateau, which is a subsided continental platform, and its area is about 300,000 square kilometers. Its tectonic history is related and connected to the plate movements of Gondwana, Antarctica, New Zealand, and Australia. In the depot centers, mainly Mesozoic, Deltaic to marine siliciclastics and shallow marine carbonates have been deposited, and the total thickness of these sediments can reach 15 kilometers. What this research focused at mainly is the Mungaroo Formation, which is a late Triassic formation, and the depositional facies of the depositional environment of this Mungaroo Formation changes from delta plain to fluvial plain to deltaic to shallow marine. Therefore, it's a quite complex sedimentary system. It provides the reservoir. Its sandstones provide a reservoir for the area. Source of hydrocarbon here is either the coal seams in the Mungaroo Formation or the carbonaceous shales and claystones of the underlying Locker Shale. Seal is provided by either the Mungaroo Formation itself, or the regional seal in this area is the Mungaroo Shale, and the Barrow group. The traps are usually tilted fault blocks. So in this research, the workflow that Adriana followed started with data conditioning, which I will not discuss today, and then the analysis of the structure and the stratigraphic framework, followed by formation evaluation, focusing at information from wells, such as logs, cores, core descriptions. Then frequency decomposition, combined with forward modeling, helped to evaluate and assess the validity of the geological models that were set up in the previous stages, and this led to the prospective evaluation stage. The first stage was structural framework analysis. This was helped by multi-attribute analysis, that is combined edge attributes, in this case dip, structurally orientated semblance, and tensor were used to create this cyan, magenta, and yellow color blend, in which the full expressions, the complete expression of the faults can be evaluated. Now, once the edges faults in this dataset have been volumetrically extracted and identified, then different calculations could be performed, such as determining the orientation of these edge elements of these faults. That helped to investigate the structural orientations, the dominant structural orientations, and at the different stages, such as the pre-rift units, the syn-rift, the late rift, the post-rift, and the passive margin rocks. In the pre-rift and the syn-rift rocks, we have dominantly the same directions or orientations. This close to north-northeast, south-southwest orientation is dominant in both units. However, in the syn-rift stage, we have additional orientations showing up as secondary orientations. This is very close to north-south and the northeast-southwest orientations. These are interpreted as being related to the en echelon faulting characteristic in this dataset. As going a bit shallower, we see the polygonal faulting showing up. And as you would expect, the polygonal faults will have the directions, will show every orientation. There's no real dominant orientation in this unit. In the shallowest part, in the passive margin sediments, a different dominant direction can be observed. That is a more east-northeast, west-southwest orientation. Although the combined edge attributes can help to identify every single lineament in the dataset, during the analysis, they were not all interpreted or turned into fault planes. Only the main faults were interpreted by Adriana, and these are the fault planes that were used in the modeling stage. As you see, all 4 wells have been drilled on tilted fault blocks around the crest of tilted fault blocks, as you see here in the Yellowglen and the 3 Chandon wells. The next step was to try and build a stratigraphic framework in order to analyze and understand the regional extent of these surfaces. 10 regional horizons have been interpreted. Some of them are easy, such as the seabed. Others were a bit more complicated. The 2 most important surfaces in this dataset or in this research were the top Mungaroo Formation, that is the green line on the screen right now, and the base of the Mungaroo Formation. As neither of the wells in this dataset reached the base of the Mungaroo Formation, another approach had to be found to determine, or at least provide some interpretation and explanation for that particular interpretation, the base of this formation, or the top of the Locker Shale. For this purpose, Adriana used a combination of different attributes. One of these attributes was the pseudo-relief attribute, and she used texture as well. Texture is an attribute that will highlight in yellows and reds in this color scheme the strong reflections which are characterized by strong variations in their neighborhood. As you see, this could help to define a lower boundary for this unit. That is definitely a Mungaroo unit here. And in Adriana's interpretation, the base Mungaroo Formation was defined as the lowermost competent layer, or the layer or the horizon that separates the units where we see stronger reflections and more variability from areas where this is not so characteristic. Other attributes and other volumes that were used in this interpretation were the envelope and the opacity blend between of the envelope and the pseudo-relief attribute. With that, Adriana got her two most important surfaces because she wanted to investigate how the sedimentary environment within the Mungaroo Formation changed through time. And in one of the later slides, I will show you the results of isoproportional slicing between the base and the top of the Mungaroo Formation. That is, 10 different pseudo-horizons were created with the isoproportional slicing tool between these two horizons, and the different shapes and forms and stratigraphic features were interpreted on them. But before that, the well data were analyzed. She used the gamma rays and the resistivity. She used the core descriptions, core photos, and of course the well completion reports that were available for this research. Based on these data sets, she could differentiate between 4 most dominant or most important stratigraphic features. That is the crevasse deltas, the mouth bars, distributary channels, and the fluvial channels. Reservoir quality increases or improves upwards in this slide. So the fluvial channels, which are the most prominent, the best quality reservoirs here, can reach a 35% porosity, a relatively low clay content, and very high gas saturation. Now, with this knowledge, the next step was to identify these elements in the 3 Chandon wells. That is Chandon 2, Chandon 1, Chandon 3. And this happened here, and between these 2 horizons I mentioned earlier, that is top Mungaroo Formation and base Mungaroo Formation, the isoproportional slices were created, and the high definition frequency decomposition color blend was draped on these horizons. And as you see, the interpretation here, based on these isoproportional slices and the results of the color blending and frequency decomposition, different channels could be identified. So they were grouped into large, medium, and small channels based on their width, which can be seen can be measured on these slices, and based on their thickness. Some of the thickness obviously can be determined from the well logs themselves. However, the high definition frequency decomposition is a good tool to investigate thickness variations in a very precise manner in the seismic data set. With the help of these slices and the information on them, Adriana was able to fill in the gaps between the wells to determine how the fluvial channels distributed, and when they turned into more like distributary channels, and then how mouth bars evolved, and then how this whole unit reached the pro-delta phase. The evolution of these units can be seen on these 2 block diagrams. So the delta plane fluvial system is characterized by these large-scale channels and channel belts and vertically stacked channels, and in between them there are shaly rocks. And by the end of the Mungaroo Formation deposition, it reached the pro-delta, distal delta phase. Next step was to try and model the frequency responses that are observed in this data set and tie them to different variations in the different parameters. Is it geometry related? Is it rock property related? Is it fluid content related? To start with, 4 individual models were set. One through Yellowglen and one through each Chandon wells. And how this modeling is performed. First, the well logs were interpreted in with the help of rock physical templates. These data were available in the dataset, so Adriana had access to the VP, the P-wave velocity, S-wave velocity, density measurements in these wells. And with the help of these, she could differentiate between the different sandstone and shale units in the wells, and could precisely determine that the layer 4, this pinkish color, was the most gas-bearing sand. The other end member was the layer 6, which is a water-bearing sand. These rock physical templates also helped to determine internal variations or internal differentiations between the reservoir rocks here. Once these internal boundaries were determined in the wells, an Earth model could be built, obviously following the seismic data as a guide. So the main seismic horizons were taken into the model, but the internal layers, which are not always defined or resolved or shown by the seismic, were also taken into the model. For the rock physical properties in these layers, Adriana had to perform fluid substitution as well, based on Gassman's equation. Why was it necessary? Well, for example, in layer 4, there are only information about the gas-saturated sandstone, the density, the P-wave, and the S-wave velocity. So in order to be able to extend and propagate parameters throughout the same layer, but in the water lag, she needed to run fluid substitution. And this is where you see the original data measured data are represented by the black line, and the fluid substituted are shown in the green line. Here in this layer, that's from gas to water. Once this Earth model was created, a wavelet can be run through this model, therefore achieving or producing a synthetic seismic data set. And the correlation between the synthetic seismic section and the real-life seismic section is proper high in this data set. So it is clearly reproduced the key elements, the key seismic surfaces and reflections. Another dimension to check the validity of the synthetic seismic data is if we run frequency decomposition on this synthetic data set. And the results of the frequency decomposition, which use the same parameters as the original frequency decomposition performed on the real-life data set, which is shown in the top. So with that we can compare how much the colors are represented or reproduced in the synthetic model. Usually the fit is not perfect. It is very hard task to create a perfect fit throughout your model. So what we usually focus at, and this is what happened here as well, is the neighborhood or the close vicinity of the well here. And what's important in our experience is to look at how the colors change, so the succession of the colors and shades, how they transition from one into another. In this panel on the left-hand side, you see the original high-definition frequency decomposition color blend. On the right-hand side is the synthetic counterpart. And what's important, again, to point out is that this transition from the orangey reddish to greenish bluish and darker greenish system, the colors and hues, and then at the gas-water contact, this whole system changes from orangish, brownish dominated into something more on the blue end of the spectrum. So as a conclusion, it can be said that the flat spot, that is quite obvious in the seismic data set, was validated as a gas-water contact by the synthetic seismic modeling, and the frequency decomposition shows the frequency decomposition of the synthetic seismic section results in a similar succession of colors, and it reveals a distinction of clear distinction of the green-red tones above the gas-water contact. Another challenge, and it's a bigger challenge, one must admit, was to create something across the 3 Chandon wells using a similar approach, which I will not explain again. And with the help of parameters that are validated and proven around the wells, in the vicinity of the wells, a regional cross-section was set up. It's an arbitrary line that incorporates all 3 Chandon wells and tries and investigates how parameters, rock physical parameters, can be transitioned or propagated away from the wells and between 2 wells. How precise, how correct this approach can be. The synthetic data show fairly good correlation with the real-life real-life seismic data set, potentially with the exception of the Chandon 3, where small sort of discrepancies have been found. And the frequency decomposition results show a similar correlation as we've seen in the Yellowglen. So these greenish reddish tones of the gas-bearing sandstones are preserved and are reproduced by the synthetic data set. If we focus at the long regional section, now this is where we see some inconsistencies. And it's not always easy to explain why why the differences are there between the real-life seismic and the synthetic seismic, or the real-life color blend and the synthetic color blend. One explanation that is very likely relates back to those isoproportional slices and that model that I showed you earlier in a previous slide, where we've seen that between the wells there's a great variation. There are so many channels, different sizes, different thicknesses, stacked and unstacked channels or non-stacked channels. But this geometrical and lithological variation couldn't be represented in this model. It's not that it physically couldn't be represented, but due to the limited time available for Adriana, this just was too much for this research. So in this model, the rock physical properties defined for the different layers at Chandon 2 and Chandon 1, for example, are linearly transitioned from one well to another, and they do not take into consideration any other geobodies in between the 2 wells. I'm quite confident that at a further stage, the inclusion or the incorporation of these geobodies could have improved the results significantly. And a question always arises, what are these frequency responses are sensitive for? So we know they are driven probably by thickness, changes in lithology, changes in pore volume, changes in pore fill. So how sensitive they are, in fact, to these parameter changes. The Yellowglen area offered a good test region to investigate, for example, how fluid content changes the frequency responses. This is a map from the original well completion report, and it shows that a gas-water contact was identified between the Yellowglen fault block and around the Yellowglen fault block and the not a tilted fault block that's referred to as upside block here. We see the two tilted fault blocks along a section in this image. What we see is a very different frequency response in the Yellowglen fault block and in the upside block. Neither of the reddish-greenish colors appear here. An explanation should be given for this. There might be different approaches. In Adriana's case, she investigated whether the color changes, again from this reddish-greenish to the more blue-dominated hues, if it can be related to changes in fluid content. So with the help of the fluid substitution functionality, she started to change the gas content of this layer 4, that is the best reservoir sandstone in this well. And what we can detect is the change in gas content, or change in water saturation, from 0% water to up to 2 to 5% water saturation. It can reproduce this shift from this darker greenish reddish, it's reddish more likely here, into the blue hues. When the fluid content reaches this 5-2% of gas, so the gas content decreases and the water content increases to 95-98%, this color shift can be detected, and this results in very similar blue and purple tones. Although the synthetic seismic is not shown here, even 5% gas content could reproduce the flat spot in the synthetic seismic data. So based on this finding, Adriana decided that an interpretation for the difference in frequency responses can be potentially found in changes in fluid saturation or fluid content. Therefore, for the volumetric analysis and volumetric calculations, she excluded this upside block from the Yellowglen area. Another important parameter that definitely drives the frequency responses is thickness variation. And the thickness variation can be easily investigated and analyzed with the help of a wedge model. In this wedge model, the rock properties were defined coming from the well, and we again focus at the layer 4. So the rock properties, as I said, are determined from the well log, and they are thickening to the right and thinning to the left in a linear manner. So the same succession of rocks and same succession of rock parameters are stretched or squeezed into a wider or a narrower zone. This helps us to determine how thickness changes would be represented by the frequency, by the colors. If we look at this bottom left panel, we see that the original thickness, that is this greenish, bluish, reddish hue here, is turning into more likely a reddish orangey color, and then through yellow and white with a slight hint of blue in it. So if these units are thinning, this is the transition of the colors that we expect or can expect. Looking at the original real-life color blend, we see that for a while the color response is quite stable in this unit, but then as reaching closer to the gas water content, there's a shift from these hues that are here towards the reddish and orangey hues that is here. So in fact, this gas water contact and the tilted layer together act as a wedge model. So in this case, the color response, the color changes, the frequency response changes, can be explained as a thinning wedge along the gas water content, but it raises the awareness of the interpreters that if this color change can be found away from the wells, then a thinning of the unit should be considered as a possibility. So once the frequency responses have been confirmed, for now Adriana knew how the gas saturated units look like in a color blend and the other attributes. She could run adaptive geobodies to extract these units, and then the volumetrics can be calculated. The volume of these geobodies can be calculated, and they serve as an input, as the gross rock volume for the calculations, for the volumetric calculations. As mentioned before, the Yellowglen upside block was excluded from the volumetric calculations, and P90, P50 and P10 gas initially in place volumes were determined for both the Yellowglen and the Chandon area. For the Chandon area and the Chandon prospect, the numbers are very similar to those obtained by the operator in this area. Of course, in the Yellowglen area, the numbers calculated by Adriana are smaller because a significant amount of rocks, potentially water-saturated rocks, were excluded. Based on the frequency responses, we can see that there are other tilted fault blocks that might be interesting from an exploration point of view, but it's likely that they are small in volumes as compared to, for example, the Chandon accumulation. As a conclusion, it can be said and it can be concluded that the medium to large scale channelized deposits of the Mungaroo Formation have a high potential for hydrocarbon accumulation, and the rock physics modeling combined with the forward modeling, both synthetic seismic and synthetic color blends, allowed Adriana to investigate the presence of hydrocarbons within the pore space of the sand unit and their extent and their the saturation levels as well. These steps, these analytical steps and modeling steps helped Adriana to mitigate the risk of these already defined prospects and evaluate the uncertainty of these accumulations or these prospects. The definition of these elastic properties, or the defined elastic properties, could potentially be used as well in a future AVO analysis if angle stacks will be available for this data set. Thank you very much for your attention today.